welcome. Also welcome to the people from the other campuses. Thank you for joining us. We have Mauricio, who will dive into the effective developer testing. Mauricio from Adyen. If you have any questions, of course, keep them for the end, or you can raise a hand. I'm sure Mauricio will be happy to answer them. Also, for the people watching us online, we have the link. We will have the link, actually, in the comments of the live stream. You can use it to ask your questions, and we will take them, of course, at the end of the presentation. So, yes, give it up for Mauricio and enjoy.
Thank you. Folks, thanks. Yeah, let's talk about testing. Before that, a little bit about myself. So as Ada said, I work for Adyen today. And there I lead different initiatives, one of them really related to training engineers. So whenever an engineer joins Adyen, this person goes through a bunch of training so that she learns about how we do software. So somewhat connected to your goal in a way. I'm also an assistant professor in software engineering at Delft for 6 years now. My focus has been software testing and software maintenance. I teach one course there, the software testing for the Bachelor in Computer Science. I wrote a book about testing last year. It got published 2 years. I wrote 2 years ago. It was published last year. Those are my 2 latest projects, by the way. I'm not sure when there's going to be another one because one of them gives me a lot of work. And I'm originally from Brazil, although living here for 7 years now. But let me start with a story for you. And this was end of 2005. And I was working for a company that did embedded development. So you learn C++. There I was working in C. And we had a project that was all about automating gas stations. And it makes no sense today because all gas stations are automated. You go there, there are computers and etc. But back then this was not super common. And the goal of the company was maybe we can use this very small device here to automate gas stations. And we then assembled a team there, and we were like 4 or 5 developers, and because I had some previous experience with the platform, I was the lead developer. And this was the first time I was going to really lead a project from a technical perspective. So I felt, well, I'm going to make an amazing project, right? So we spent maybe 9 months coding the first version of the program, and then we decided to finally install and see it running. You can imagine that deploying this wasn't super easy, right? We had to do physical installations in the gas station so that we could communicate to the pumps and blah, blah, blah. And the company decided that the first customer would be in Dominican Republic. So for me, it was very cool. Also one of my first international trips. So we went to Dominican Republic, me and basically 2 managers. And we spent the first day doing all the installations there. And 9 a.m., 10 a.m., I don't remember, we put the software to run. I was monitoring the software, looking at the logs, and everything was fine. And I was super impressed. No bugs, no problems. I spent the whole day in the gas station just looking at how people do. Beautiful. Super proud of myself and super proud of the team. 5 p.m., no bugs. What do? Project successful. You are in Dominican Republic. It's 400 degrees. And you are in one of the most exotic places on Earth. What would you do? The same that I did, you would go to the beach and celebrate, right? That's what we did. And I remember being there also with the owner of the gas station that was funding this pilot, and the guy was paying everything for us. And he was super happy that this tool would really, save lots of hours from work from his side. I went back to the hotel, I started to sleep. When it was 4 or 5 a.m., I don't remember again, the phone rang, and I got the phone, and it was someone from the gas station saying that the software presented a bug sometime at night. And after that bug, no one could do any refuelings. So you would get the nozzle, the pump, and you would do like this, but no gas would go out of the pump. And that was sort of the behavior that we implemented ourselves, that if the software is in a crashing state, don't allow people to refuel. That seemed like the right thing to do back then to avoid, stealing gas, which was a common problem there. Then it took me a few hours to get to the gas station. We really turned it off manually. We undid the installation so that the pumps could go back to normal mode. And then there I was reading at the logs and trying to identify the bug. And I don't even remember precisely what was the case that caused the bug, but it was a software bug, of course, which I was able to patch, deploy, put it to run again. And then I spent maybe 10 days there, no other big bugs, but you know, the confidence of the client towards the software was zero after that. The guy never really trusted us anymore, so he was always looking at the software as if, oh my God, this is going to crash and this is going to destroy my life. And that was, you know, the experience that made me reflect a little bit more about testing. And back then I had done software testing in my bachelor, you know, I knew the theory of software testing. I knew JUnit. I was always a Java developer. I knew JUnit. I didn't really know CUnit or whatever you have for C, C++. But you know, I had those ideas in mind, but we were not really applying them. How did we do testing? A lot of manual testing. We had beautiful spreadsheets full of scripts that we would do manually. We even created a pump simulator so that we could try, you know, and see if the protocol that we were reading from the pumps, they were working properly. But as you can imagine, as a developer, what do? You implement a new feature, you do 1 or 2 or 3 manual tests, mostly covering the happy paths. You never really test things again. So that was sort of, to me, you know, oh yeah, I had more slides with pictures. Good that I skipped all of them. But then, you know, in the end, I just realized that testing is very important. And from there on, that was the moment in my career that I decided that I would never really try to build software without writing tests. And then that has been quite a big journey for me. And I learned a lot through this journey. And the idea of this talk is to share a bunch of very high-level things that I learned that makes me more effective. So this talk is really meant for software developers, right? And why am I saying this? If you think of testing, you can think of maybe dedicated testers whose main job is to test your application. So maybe you produce your software and then some tester goes there, maybe together with the product owner, and this person understands about the software, she creates good test cases, so on and so forth. This talk is more from the perspective of the developer. So the person that is writing the software, it is also your responsibility to make sure that the code you write works, right? So this is why it's about developer testing, which is the fancy term for the tests you write as a developer. Cool. So yeah, 11 things. Let's go one by one. The first one. And the first one that I want to say is that testing is an amazing tool. And testing code helps you to do lots of things. And you can see testing as a way to find bugs, and that's what test is for, but you can also see testing as a way to help you as a developer to take the next step in the feature you are implementing. And why am I saying this explicitly, right? Because if you look around and if you try to learn about testing, you have different clusters of books you can read about. One of them is a cluster of books written by practitioners, people that are software developers like us. They wrote books, they shared their experience. So for example, Kent Beck, when he introduced test-driven development, or Steve Freeman and Ed Price when they wrote this book, Growing Object-Oriented Software Guided by Tests. Even pragmatic programmers, right? JUnit testing, whatever for Java, blah, blah, blah. If you read those books, you feel that those books are all about how tests can help you implement your feature. More as a tool for you, you know, I just wrote this small feature. Is this working? Yes, it's working. Let me take the next step. Which is very cool, right? As a developer, I want to be productive. I want to be confident that I can take the next step. But testing is also a lot about finding bugs. This is what testing is and always was defined in software engineering. Testing is the activity you do to find bugs. And we also need to do this. And funny enough, if you read books written by academics, so theoricists in computer science or software engineering, if you read books written by them, what is the focus there? The focus there is how do you look at a piece of software and you find bugs in it. Those books are very nice. You can learn a lot from them. But they are very hard to be digested. So some of them don't even have source code. So the first one here, Mauro Pezzè, amazing book. You get, you know, all the theoretical challenges behind testing and why testing is so hard, but there's no simple code example that you can then translate to real life. And then, of course, you also have a bunch of other books that are written with the focus of testing in the software development process. How do you see this in a bigger, larger process? How do you also maybe take into consideration what the final user wants, right? That's also important nowadays that we're building lots of products. And to me, it was always about combining these things. So that's the message I want to pass, right? So if you're learning about testing, testing is not just test-driven development, you know? Testing is about finding bugs. And as a developer, what you want to do is combining all of this in your process. So something like this. You, the developer, you want to do testing to support your development. Maybe you want to do test-driven development because you like it. You want to design for testability because you want to facilitate your life. You may reflect about APIs and how you're going to design stuff. But you also sometimes want to change hats and then apply more testing-focused techniques like specification-based testing, boundary testing, and structural testing. And it's fun that when I give this presentation, and by now I've given it a few times, the techniques on the left, they are usually more popular among people than the techniques on the right box, right? So who knows what test-driven development is about? Yeah, yeah. Who has heard of boundary testing? Nice, nice. I see hands. Structural testing. Nice, nice. Definitely the minority, right? So I gave this presentation a few weeks ago in JFall, right? So the big Java conference in the Netherlands. There were like 400 people in my session, and then I could see like 80% of people raising their hands here, and then a way smaller number of people raising their hands there. And of course, life is very hard for us. Why would it be simple, right? So you have to, on top of that, besides really deciding when to, when do testing to support development and when to do testing to help you find bugs, as a developer, you have to take pragmatic decisions because you want to automate this test. And this means you have to take coding decisions. For example, do I want to mock this component, right, to facilitate my testing? Or do I not want to mock this component because I prefer to go towards a more integration testing? How thorough do I need to be when testing a feature? Your budget is limited, right? And you cannot test forever, right? This is one of the laws of software testing. Exhaustive testing is impossible. You cannot test all the combinations. What you have to do, you have to pick which combinations to test. Maybe you can test just a few, maybe, and then that costs less. Maybe you want to pick more combinations of tests, and that costs more. And you have to decide as an engineer, how much money can you spend in testing something? So this all makes your life way more complicated. Yeah? So this is topic number 1. See testing also as a way to find bugs. Now, second lesson, that is, your testing is as good as the test cases that you can create, right? Your tests are as good as the inputs you can think of using your maybe imagination, and how nicely they exercise your program looking for things that maybe the developer that wrote the program didn't think of. That's how you find a bug, right? That you find a path in your program that no one really thought about so much. And it doesn't matter if you have lots of tests if all your tests are crap, right? If all your tests are always green and they don't find bugs, your tests are not really paying off. So your tests are just as good as how good your test cases are. And then the question is, how to create good test cases? One way of doing this is to try and be more systematic about how you look at a program and how you explore this program, looking for nice inputs to give to it. We wrote a paper a few years ago, people in Delft and people in the University of Melbourne, and the goal of this paper was we observed a bunch of engineers creating test cases. So we gave them programs and we said, write test cases for this program. And those programs were just, normal utility functions you write when you're learning how to program. Think of an index of function that receives an array, and then you have to return the index of the whatever char integer that you pass to, that you're looking for. So think of this type of functions. They had 20 to 30 lines of code, a bunch of ifs, a bunch of loops, and we told them create test cases. And they were thinking aloud, and we were able to see how they reason about this. And then we observed a couple of things. One of them is there were two clusters of people. People that would look at the requirements of the program, and they would create tests based on the requirements. So we gave them, of course, documentation of what the method does. And these people kind of blindly ignored the source code. They looked at the requirement, and they created test cases. Very cool. Requirements are very important. You want to look at the requirements. They are the source of truth. So you can create test cases. The other cluster of people, they looked at the source code. So they completely ignored the documentation that we gave to them. And they looked at the source code and they said, there's an if here. Let me try to exercise this if, which is also very important. Your source code gives you information that you can use for testing. Just one person actually used both. So the person was like, let me look at the requirements. Let me look now at the source code. So the combination is key there. So to create good test cases, you have to use a mix of what you learn from your requirements plus what you see in the source code. And the second finding of this paper was that developers were very little systematic about it. They would, look at the piece of code or requirements, and they would like, what should I test next? And they would just, randomly come up with a test case. They would implement this test case, and then what should I do next? So they weren't really following any systematic process that you could see they were being thorough, and they were not gonna let a test case slip through the cracks, right? That's why you wanna be systematic. That's why other professions actually are systematic. They don't wanna let things go on the cracks. There's a very nice book that is called the Checklist Manifesto, and this book actually lists the advantages that you get once you're trying to, for example, create checklists to make your work more systematic. Research shows that, for example, medical doctors that use checklists before surgeries, they make less mistakes than doctors that just follow their knowledge. Both doctors know the same thing. The difference is that, one is being systematic about how they are approaching the task. So we can try and be a little bit more systematic when it comes to test cases. I'm not going to mention techniques here, but you can think of the specification testing technique that I mentioned in that box is a technique that helps you look at the specification and explore it in a more systematic way. If you look at the source code, I'm going to talk a little bit more about source code, but you can also look at source code in a systematic way so that you are sure you didn't miss anything. If I try one more time to explain to you why, it is nice to try and be more systematic. Being systematic is a behavior that you see in more senior engineers. And research shows that when they try to understand how senior engineers tackle a problem in comparison to more novice engineers, a big difference is that seniors are more systematic. They tend to know what to do next, and they're just following some recipe that is maybe in their minds. And this is sort of illustrated by this figure. So this is a graph that tries to illustrate how seniors tackle a problem, and this is how novices tackle the same problem. And in here you see that things are going everywhere, right? Meaning the novice is exploring. She doesn't know where to go, so she's just going everywhere. And here you see that seniors are more linear towards what they do. Cool. Now the question is, being systematic is nice. That's going to help me look for more bugs, come up with better test cases. Should I be systematic all the time? Because, being systematic has advantages, but the clear disadvantage is that it just costs more time and more money from you. Of course, the answer is no, you don't have to be systematic all the time. And it is easy to understand this by simply trying to understand how software behaves. Lots of research shows that if you try to understand the complexity of your software systems, you sort of see a power law in the distribution of complexity. What does this mean? Imagine that this is complexity, so the more towards this side of the figure, the right side of the figure, the more complex a function is or a class is. And the y-axis is the number of methods that has that amount of complexity. And what you observe is that most code in your code base, they are very simple, right? Think of your code right now and try to think of each individual method in your code base. I'm pretty sure most of your methods, they have, 5 to 10, 20 lines of code or something like that, 1 or 2 if stops. Just a few of them are really, really super duper complex, but they do exist and the tail is very long. So there are lots and lots of complex methods, and maybe that's a way for you to prioritize when to be more systematic. Simple methods like this, you probably look at them and then you can see all the interesting test cases that you need to exercise there, but for more complex ones, maybe you need some extra help. So this is a trade-off or a decision-making process that I have to myself, that if something is simple, I'm fine. If something is more complex, I definitely know I need something fancier. Research also shows, if they try to look at bugs and how bugs are distributed in your code base, if you split this by complex methods versus simple methods, guess what? Complex methods are more likely to present bugs than simple methods. So that's why you also need to put more efforts here. Bugs are interesting animals, right? They like a special type of situation in your code. They don't live in happy paths, right? Because we're very good at implementing happy paths. Bugs, they love to live in boundaries. What do I mean by boundary? So imagine that you have your program, and this puzzle tries to illustrate the different parts or decisions that your program makes. As soon as you move from one piece to the other, that's a boundary. So maybe a source code, imagine you have a simple program, it gets a number from 0 to 10. If n is bigger than 5, then it's time to eat bitterballen. And if n is else, then it's time to eat apple pie. So if n is 4, then it's apple pie time. If n is 5, it's apple pie time. If n is 6, it's then bitterballen time, right? And the boundary is here. Because, you know, there was a very small change in the input of your program, right? Or a small variation from 5 to 6. You know, it's just a +1 here. But your program did something completely different. So this is basically a boundary. And research says that bugs love to live in these boundaries. But there's a solution for it. And the solution is, as long as you're able to identify those boundaries, of course, in a simple program like this is pretty straightforward. What do is you write tests for the boundary. And you test as close to the boundary as you can. So if I were to test this program, I would not come up with 2 random numbers. One that makes my program to return pi and one that makes it return bitterballen, right? Because that's what we usually do. You see an if, you think of a random value that makes the if true and a random value that makes your if false. What those papers are saying is you have to pick values that are as close to the boundary as possible. So for example, in here, 5 and 6 are the test cases you want to have in your program. And it's very nice, very easy sort of to see why those numbers are better than a random number. So imagine that you picked as a developer 2 and 42. If a developer by mistake comes here and changes this greater than to greater than equals to 5, your 2 tests will still pass, right? So your tests were not able to review this bug. Whereas if your tests are like this, n equals 5 and n equals 6, and the developer comes here and introduces the bug, one of the tests will fail, right? Because the test will be expecting, I don't know, bitterballen, and the program will return apple pie. So testing near the boundary just makes your test a little bit more strong. And this is a very easy tip for you to follow as a developer, right? Now, of course, the challenge is to identify those boundaries. This is very simple in a program like this. In a larger program, this can be a little bit more tricky, but it's an exercise worth doing, right? Look at your program, identify the boundaries, test the boundaries. Number 4, code coverage is a good tool, yeah? And it's really fun because I feel like I've spoken about testing to so many developers through my career, and there's a common feeling that code coverage sucks. And even in the Twitter bubble, right? So if you like Twitter and you follow developers on Twitter, I'm pretty sure you've seen some discussions saying that, yeah, code coverage is useless. And people have lots of arguments for that. For example, they say code coverage can be easily tricked because, you know, I can write a test, I can remove all the assertions of my test, I will get 100% code coverage, but I'm not testing anything. So it's a metric that is very easily tricked. Or they say, you know, my company forces me to have 90% code coverage, and that means for me as a developer, I have to start writing useless tests. I wouldn't test this getter, for example, but now I have to, because otherwise my tool will break my continuous integration and blah, 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 right? So, and 100% coverage, you know, I'm gonna put a lot of effort, I'm gonna get to 100% coverage, but that doesn't really mean that my software has no bugs. So if the number is saying 100%, but still I have bugs, why would I want a metric that doesn't really tell me the truth? And of course, all those things, they can be a little bit true, but then I'm gonna argue that let me blunt, you're not using code coverage properly, right? If those are the things that are making you suffer, it's just you're not using the tool in the way that the tool was supposed to be used. How code coverage is supposed to be used? Not as a magical number that someone defines to you and then that you have to blindly achieve, right? So putting 80% coverage for all your software, maybe it makes sense, but maybe not, right? So it's not just a magical number you want to get to, but you want to use code coverage to reflect about how good your current tests are, and then you learn from it, and then you improve your test suite. In an illustrated way. So you are the developer, you are implementing this new feature, you're going to write some production code, maybe you're doing test-driven development, maybe not, but then you're implementing your code, you're writing some tests, and you're using tests more to support you rather than anything else, and then at some point you're like, I'm done with the feature, let me do some proper testing now. And then you change your hat, and then you do specification-based testing, you reflect about the boundaries, so on and so forth, and then you end up with this beautiful test suite. Now the question is this a good test suite or not? What you can do is you run code coverage, and then you look at the report, and the report will say, you're missing this line over here, or you're not covering this branch over there. And what do? You reflect, why did I miss this case? Because I shouldn't have missed this case, right? It is in the specification. I developed this if myself. Why didn't I test it? And then you reflect about it, and then you decide. Maybe the decision is, yeah, it makes no sense to test it. It's just a lot of work. It makes no sense. Or, oh, yeah, I just forgot about it. I don't know why. And then you write the test. So see that there's no number anymore using code coverage like this, right? It's more like a tool to complement the test that you wrote. And if you read more theoretical books, that's how it is meant to be. And then, at some point you're done looking at the code coverage reports, and then you're going to say, yeah, I think I'm done. I created all the tests that I could. I augmented my test suite to the best that I can. It's time to push to production. So code coverage should be a tool that assists you in deciding if your testing is good enough, and not a tool that takes this decision for you, as you see tools trying to do this, right? They break your CI if some random number is not achieved. That makes no sense to me. Yeah, I will come back to using a number or not, because I think this is relevant, but before that, let me try to answer this very important question, right? Okay, but code coverage is cool. Do we see a correlation between higher code coverage and better test suites? Because that's what I expect, right? So if I keep writing better tests and if I keep using code coverage to create more test cases, hopefully I'm doing this because I'm making my test suite better. Is this true or not? To our happiness, yes, lots of empirical studies show that there is this correlation between code coverage and how good your tests are, and how those experiments usually work. So what they basically do is they get a program, they create test suites in an automated fashion, of course, test suites achieving different levels of test coverage, so 60%, 70%, 80%, so on and so forth. They then introduce bugs on purpose to the production code, and then they see which test suite catches the bug. And what they observe in large scale is that as soon as you're close to 90% in case of this paper, that test suite is able to review most of the bugs that they introduced in the program, right? And this research was made by Siemens, so not academics, fully academics doing this. This is funded by a company. And then this was 1994. The world was much simpler back then. Brazil was the best in soccer. We won the World Cup. Things are very complex now, I don't get it. 2009, we learned a lot about how to make experiments in software engineering, right? So as a community, academics are learning how to do these experiments. Many years later, you see replications. Those replications, they also identify correlation, although not really linear correlation, right? So there are other factors into play, but you always see this correlation happening. Right? So coverage does make sense, and in the worst case, going for a larger coverage might not be such a bad idea after all. 2014, yet another paper with similar discussion. One interesting stuff from this paper is that she shows that sometimes coverage is not really related to effectiveness, so it's possible for you to have a test suite that has high coverage, but a lot of bugs still slip in. Complex systems are complex, for sure, but coverage can be really useful to identify under-tested parts of your code base. And I think that's how you can use code coverage metrics in a way, right? So if you just run a code coverage tool and you look at numbers right now, even without a lot of context, definitely, if there's a module in your system that has 20% coverage, what you can say about this is that testing there is lacking, right? It doesn't matter what type of software you have, 20% is a very low number. So that's how you can try to use numbers, right? To identify under-tested parts of your code base. So high coverage may not mean much, but low coverage means a lot. So that's what I just said. And now if I come back to numbers, should we define numbers in the continuous integration or not? I think that's a very team decision in a way. I know many companies that do. And to be honest, I think it really pays off when your tests are already very good. You know, so you have lots of tests, lots and lots of tests. The magical number there in the CI, blocking people from submitting code without tests, will just help. So I know, I'm not sure if I can mention, let's say a very important communication software we all use in our cell phones with a green logo. The server of this application has 99 point whatever % coverage. And no engineer can make this number down. And that makes sense for them. They are very good, they keep the quality high. Now, if you're in a software system that has very little coverage right now, no tests, and what you want to do now is to write tests, this number will more block you than help you, right? Because then the CI will be always blocked, because if the coverage is low, maybe it's also because it's very hard to write a test. Life is very complicated in large-scale software systems. So I think you should put a number when things are good. When things are not good, you have to, you have more work to do before the metric, the random number without context, can pay off. Rule number 5. So one of the big discussions you see in the community is people that say that they love unit testing and people that love integration testing. Just for completeness, I'm going to define those. So unit testing is when you want to test just one unit of your program and you want to forget about the rest of your program, right? So you want to test one class and you don't care about the other 300 classes of your system, and maybe you don't even care how about they communicate with each other. You just want to focus on one unit and exercise it. Some people love it. Others say, well, I prefer to test my system in a more closer to reality setting, which means all my classes working together. And this is an integration testing. And there's this big dispute between which approach is best. I think that's a very nice discussion for the 2000s, but for 2023, this discussion makes a little bit less sense, because something that we learned in practice is that the level of the testing per se matters a little bit less. What you definitely should focus all the time is that you write tests that run very fast. So you want those tests to run in a few milliseconds. And you want tests that give you good feedback. Why do you have tests? You want tests to break as soon as a bug is introduced in your program. So you have to write a test that gives you feedback. So why tests should run fast? Because in large-scale software systems, if you start to write very slow tests all the time, that's going to consume hours of computers to run those tests. Let me give you an example. At Agin, we have lots of unit tests and lots of integration tests. If we want to run all our integration tests now, if I just press the button run, this is going to take more than 100 hours of computation time to run our integration test suite. We have 800 engineers producing code, and these people open lots of merge requests in one day. Imagine that we want to run all integration tests and merge requests. How many computation hours can we spend on this? That doesn't, now imagine Facebook and Google with thousands of engineers building stuff. So if your tests are slow and your approach of writing tests is to keep creating slow tests, this will not scale anymore. Even at Agin, for example, we cannot run our integration tests during the merge requests. We run them every 4 hours, right? And that sucks, because maybe we merge something and then 4 hours later, an integration test breaks, and then good luck finding which merge requests broke the test. So slow tests just make your life harder. So what you want to have is tests that run very fast, because then you can pay computers to run them 1,000,000 times a day if needed. Feedback. Why am I talking about feedback? Because the discussion about unit testing versus integration testing should be approached with this angle. It doesn't matter if you're going to go for unit or for integration tests. You want to go for the test that will give you more feedback. So depending on the problem, maybe unit tests are good enough. For example, if you're implementing something very algorithm focused, right? So imagine You know, you're just implementing this thing that receives inputs and then it does some complex algorithm and then it produces some number in the end. Maybe you don't care about the rest of the system and then you can just focus on that algorithm and you exercise it very well. In other situations, you're building this enterprise application and the feature you're implementing is all about going to the database, getting data, changing this data bit, sending it back to the database. So there's no algorithm complexity in what you're doing, but there's just a bunch of moving pieces and you have to send data here and there. For this case, maybe what you want to do is test all of this together to make sure that this interaction between different components work. So it's all about getting feedback. I think a book that brings this discussion in a very clear way is the book written in 2018 by Google, Software Engineering at Google. Funny enough, this book is basically, you know, they gave to different engineers at Google the responsibility of writing a chapter on an important software engineering topic at Google, and testing has 3 chapters in this book. That's how testing is important for the company. And in one of the chapters, there's this big discussion there about defining what a fast test is, and they also they use a similar argument that unit tests versus integration tests don't matter so much. At Google, according to this book, they have very strict definitions of what a fast test is. And for them, it's even a fast test. A test needs to run in one JVM, in one single thread. That's what a fast test is. And then you can go to different levels, of course, but then you're just making your test a little bit more slow and a little bit more complicated, right? If suddenly your test uses 2 threads, then maybe you're testing some multi-threaded program, and then I hope God helps you there. It brings a lot of other challenges, right? So you should tackle this in a different problem. So I think this is what matters today. So forget about this unit testing versus integration testing definition and focus on your tests. They have to be fast, and you have to take decisions for this to happen. It needs to be easy to be written. It needs to give you the right amount of feedback. Now, talking about this point over here, it needs to be easy to be written. This is something very hard to do, to be honest. As soon as your application starts to scale, or your company starts to scale, and then suddenly you don't have one team now that is responsible for a product, but maybe, you know, in the case of Agile, 80 different teams that are responsible for the product, and then what happens is this team A builds product A, team B builds product B, but then these features are somewhat connected, so module A sends messages to module B. Suddenly you have this very complex dependency of modules that talk to each other. How do you test this? For example, this is illustrated by this figure, right? So imagine you have different systems in your company, and those systems change messages, and this doesn't even have to be, you know, distributed via network, right? So this doesn't have to be a service-oriented architecture, microservices, or whatever. You can think of this as different, maybe libraries talking to each other, right? Modules. And then you have this feature that, you know, system A sends a message to B, system A sends a message to C, system C sends a message to D, and then this all gets back to A, and then A finishes the business process that A is trying to model. How do you test this, right? How do you test that this feature works? I think for many years, it was very common to approach this as, let's just do an integration testing. Yeah? So let's just try to make a test that will call system A. The test will really make a call to system B, to C, to D. When the message gets back, we make the assertions in our test. And let's just pay all the effort that is to write a test like this, meaning I will make sure that when this test runs, system B is running somewhere that I can send a message to system B. And the same for C and D. And whatever databases B, C, and D need, they will all be set up for the test. As you can imagine, this doesn't scale, right? It doesn't scale in terms of speed, so you can imagine this is a very slow test to run, but also from a developer perspective. At some point, this can become really complex and you're not really able to see interesting test cases anymore due to the complexity of this. At Agile, we have integration tests that touch 11 different systems, right? And the engineer that wrote it was amazing, right? I would never be able to write a test like this that touches 11 systems because I think I would be too lazy to do it. You know, like you have to put data in 11 systems so that they know what to do in that test case. I think the more common approach nowadays is to divide to conquer. for example, you split the complexity of the testing. And so you test your system A, you test your system B, you test your system C, you test your system D separately. And then later you ensure that the contract that is established between these two systems is kept, right? So you do what we call contract testing in a way, that your system C offers this API receives this input and produces this output. And you test that this is true forever, and if system C changes the contract of the API for any reason, then system A gets notified. This is, on one hand, very sad, because now our tests don't really see the whole picture, right? We're not really touching everything, but it's the way to scale. It's the only way to make developers productive. But and at Agent we approach things like this, for example. But does that mean you don't write integration tests anymore? Of course we do, right? Because we also want to see all the pieces working together in a way. But those are the minority, right? And those tests are more to exercise important paths of the application so that we're sure they don't break when we put them in production, rather than using integration tests to exercise every branch of your program, right? An if is better exercised in a unit test or in a fast test, not in an integration test. So it's a change of mentality that you see, especially now in the microservices world, right? I know a lot of people disagree with this, but I'm still trying to find a place that was really successful in testing complex systems via integration tests only. As soon as you distribute things, distribute not only in the sense of distributing maybe via network, but distributing teams, right? Different teams building software for you. That becomes a people problem that I cannot see being solved by integration testing. Now, the other thing is testing has to be very easy, otherwise people will not do it. So, the best way for you to convince your team members to write tests is to give them mechanisms for writing tests in a very simple way. I'm going to give an example of a project that was developed at Delft. We have this program called Andy. And Andy is the program that assesses students. So students submit code solutions. In this case, students submit test solutions, so it's for my testing course. And Andy gives a grade of how good your tests were. How does this work? Students submit test code. We get the test code. We compile the test code. We run the tests that are here. We calculate coverage. We calculate mutation testing. We check the code of the student against some rubrics that the professor wrote. We do some static analysis to ensure other things. It gets all this information together and it produces a number in the end. So this is what Andy does. When we were trying to test this thing, we quickly decided that unit testing the modules was not a very good idea. Because if we somehow don't compile the code, yeah, let's simplify things, let's not compile the code. Then if you don't compile the code, you cannot run the tests, right? You need bytecode to run the tests. And if you don't really run the tests, how can you calculate code coverage? So for us, the decision was these components should always be executed in any test case. Do you have unit tests? Yes. So for example, the rule that calculates the final grade, right? Given all the inputs of these different components, this is super unit tested. But most of the tests, they really use the real components of our engine. And then writing this test was something very hard. Because, you know, we are really compiling code. We really call Java compiler, and we really call JUnit to run the tests, and we really call Jacoco to run code coverage. So, you know, the complexity started to scale. What did we do? We created our own API to facilitate how we would create tests. So now, basically what you have to do as a developer to test the whole engine is you call this method run that is provided to you. So we created this method. This method receives 3 parameters, but I'm going to focus on the most important ones, these 2, which are the real inputs to the program. So this is the program that the student should test. So imagine just a Java class with a method and a bunch of lines there. And this is the submission of the student. So imagine 2 or 3 JUnit tests the name of this file says it all. So there are some tests that are failing, right? So imagine that the test of the student actually fails. It doesn't pass. As soon as you call this method will find these files in the right directories that they are. This run method will copy it to a temporary directory created just for this test. And we point the engine to this directory. It's all transparent to the engineer. You don't have to do anything else. You just give the names of the files and this method does the magic. This method then returns this result data structure. And this result data structure contains basically everything that has happened in the pipeline so that people can do assertions like this. Result.getTests succeeded should be equal to the number 1. And how many tests were executed? 4. So 1 succeeded. Out of the 4, 3 failed. And that the failing test has this name over here. Meaning it's very easy for the engineer to make the assertions he or she wants to make. Yeah? And note that this was something that didn't appear out of thin air. We spent some energy creating this API to make sure that we could easily test afterwards. And the funny thing was, in one of the years, I hired a bunch of first-year students to help me with this tool. And suddenly, they started to submit merge requests with lots of tests. Why was that? Because it was just easy, right? It was very easy for them to pass inputs to the program and make the assertions. So that's what you want to have. You want to be in a place where writing tests is easy. Now, the tricky thing is that this is not going to happen by magic, by miracle, right? At some point, as soon as your application starts to be more complex, testing it will start to be more complex as well. You will have to put energy there so that this becomes easy. And this was one experience at the university. I also have a funny story. That was 2013 or 14. The company I was working for was hired to give a consultancy to a company in Mozambique related to testing. And when we got there, they were building this beautiful application in C#. And the application was societally very important for Mozambique. It was the application handling all the donations that countries do send to Mozambique, and then it would control how this money is spent. So, yeah, very important application for society there. And they were suffering with tests. It was very hard for them to write tests. And it was a web application. Back then, basically what we did was we helped them create a small API. Oh yeah, and why was it hard to be tested? So imagine that the domain, the business is complex. So for whatever test you wanted to make, you would have to create, I don't know, a dozen things into the database. A donation, and then this is how the donation is spent over the months, and this is, you know, whatever that would happen in the business. So creating all this data was very painful for them, and consequence was developers were not writing tests. So basically what we did was we helped them create a small API that would just help developers to create data for their tests. And I remember we were talking to the lead engineer there, and the person was like, this is insane. We're going to spend days coding something that will only live in our test suite. This, you know, this is not really delivering any business feature, it's just testing. And I said, yeah, but that's going to really help you to write tests. But then they, you know, we were able to convince them. They paid for the investment, and then in the end, it was very easy for them to write tests. And that sort of become our, back in the company that I was giving consultancy for, sort of our routine type of consultancy in testing, because most companies, as soon as it becomes complex, writing tests become complex. So they have to put some effort to make it very simple. Those partial slides are just basically what I said, yeah? Lesson number 8. Another big discussion, things that you would see in the community, should I do test-driven development or should I not do test-driven development, right? And you see some people that are in love about test-driven development, and they say that if you don't do test-driven development, you're not a real professional. Bullshit, right? So, you know, I feel like all these tools, they help you a lot, but you gotta understand why they help you. And in the case of test-driven development, I think the whole point of TDD and why people love TDD so much is that it's not because you're really writing the tests before, but it's because test-driven development is forcing you to work in small sessions. So you're just writing a small piece of code, and you get quick feedback because you run your tests, right? Very often. And if you compare to the way people would do software before test-driven development, the way that I did for many years was I would spend hours and hours in very long coding sessions in my production codes. And then later I would try and write a test. And that is not productive. Test-driven development showed to me that you can do things in small steps and that you actually benefit from working in small sessions. So you code a little bit, you test a little bit, you learn from the feedback of your test, you repeat. If you write the test before or the test after, doesn't really matter so much. And this is coming, to be really honest, when I started to really practice test-driven development, like for real, maybe 2009, 2010, I think I did it 99% of my time, right? I tried to be really rigorous about myself. Let me do test-driven development, I believe in it, and etc. Today I do way less because I feel like it simply got to me that if I just work in small sessions, maybe sessions is not the best word, but in small iterations and I get quick feedback, that's good enough. And funny enough, if you read papers about test-driven development, and especially the more recent ones, for example, the ones done by Davide Fucci, an Italian researcher, did his PhD all about test-driven development. Today he's a professor, I think in Finland, still working on test-driven development. If you see the most recent papers from the guy, which is to me sort of the best researcher on the area, you see similar findings in his quantitative papers. People put people doing test-driven development in one side, people not doing test-driven development in the other side, and in the end, they don't see big differences in what they produce. Besides, of course, developer happiness. People working in small bits, they feel they are more productive than people working in longer bits. And this is a quote from one of his papers, that the benefits of TDD may not be because of the test-first dynamic, but rather that for the TDD-like processes, they encourage fine-grained, steady steps that improve focus and flow. So I fully agree with this, and I feel you should, as a developer, you should find your own way to get to this. Fine-grained, steady steps all the time that improve focus and flow. And I mentioned more recent studies. Maybe you're asking yourself, what about old studies? Old studies, they have similar findings, right? People have been trying since 2004 when the book was written to put people and do controlled experiments with people. Very few experiments show differences in the group that does test-driven development. And when there is a difference, this difference is sort of small, not something super significant. So TDD doesn't make magic, right? Maybe something, one more thing. Almost there, it's just 11 folks, I promise you're going to survive. Making code testable is something that I learned that is fundamental if you want to scale testing. If you keep writing code that isn't testable, it's going to be just very hard for you to test. What makes code testable? 3 things, if you ask me. Let me start with these 2, observability and controllability. I love these 2 terms. So observability is all about how easy it is to observe the behavior of what you're trying to test. Why do you want systems that are highly observable? Because you want to make assertions, right? And your tests are as good as your assertions. Your assertions will be as good as the type of questions you can ask to your program after it executed something. So it has to be very easy for you to make good assertions in your tests. How do you make this? You make your code observable. That means that explicitly when you're designing your classes and methods and so, you have to actively think, there will be a test, and this test will want to know if this class did the right thing. What type of information can I give to my test, and how will I give this information to my test so that the test can make good assertions? Controllability is the other perspective. That is, I want to be able to control the components, because in a very complex test, let's say you're testing some complex business features, some business feature that has, 10 steps or so. And for one specific test, you want to start on step number 3, and you want to have this data into the database, so on and so forth, so that you can really try the case that you want to test. It has to be very easy for you to control your system and say, hey, now you are in step 3, and this is the data you have. Run. This is controllability. And you have to make it easy for you to control. If you don't, it's going to be very hard to write tests. How do you get control? Maybe you mock a component that is very hard to be controlled. Maybe, you know, your application talks to some external system, maybe to PostNL. You don't control PostNL so much. Maybe you put a mock there so that you get some control. Maybe you purposefully insert stuff in your code so that you can tell your application, hey, go to this state. Skip the first two states. Go directly to this state number 3. If you do this, testing will be easier. And finally, the first bullet point here is, in real life, your application doesn't live in the vacuum, right? So you probably talk to external stuff, like maybe your application sends an email, maybe your application consumes a web service, it goes to a database, so on and so forth. If your code mixes business rules with infrastructure-related stuff, you know, imagine your code and then suddenly a SQL query that goes to a database. You just made your life harder. You want to separate these two things. Domain code, so the code that expresses your business rule, from the code that goes to databases or web services and etc., right? If you do this, then testing things just becomes much easier. And there are so many different names for this type of architecture out there. The one that I like is hexagonal architecture or ports and adapters. You Google for it later. But the ideal is this is the hexagon, and inside of the hexagon, you're only allowed to put business rules and classes that belong to your domain. There's no infrastructure-related stuff. You will never see a SQL query in a class that is inside this hexagon. But then you need SQL queries, right? Where do you put it? You put it outside the hexagon, so in classes that are outside of the hexagon. So for example, this cart hibernate data access object. Hibernate is a Java tool for data access. So this is full of SQL now. And then you need to send a message from here to here. How do you connect these two worlds? The database world that is full of SQL and maybe specific APIs from Hibernate to your beautiful and clean domain objects. You create something in between that is called ports. Imagine that this is just an interface. And this interface is sort of what allows you to communicate from your domain module to the outside. So this interface speaks business language, and it uses, you know, classes from the inside of the hexagon so that your code doesn't get contaminated with, in this case, database stuff. So you really separated these two things. Maybe another name for this way of thinking, maybe a little bit more modern, people like it, clean architecture, right? The book of Bob Martin, if you read the clean architecture book, you're going to see lots of effort in also separating infrastructure from domain codes. And it's not so complex, right? So you just really make sure that your domain is in one side, infrastructure is in the other. If you do this, your life will be so much easier. It's much easier to do this today than 20 years ago, to be honest, because if you use a framework, so you're building a web application, you're going to use Spring Boot or Ruby on Rails or whatever you use in your language. Those frameworks are today more opinionated towards this type of architecture. So mixing things up, you have to put some extra effort. In the past, if you think of old technologies like, I don't know, Enterprise Java Beans or JSF, web forms from Microsoft, it was just so much easier to make this mix. Today it's a little bit harder, but you know, you should never underestimate the ability of a developer to write untestable code. And what happens if you don't think of these things? You just created something that is very hard to test, and if it's very hard to test, developers won't test it. Thinking of testing in the bigger picture, you're gonna be writing tests, and more tests, and at some point your test suite will be huge. At Adyen, we are on the scale of hundreds of thousands of automated tests, right? So that's our scale. And they run in our merge requests, right? And we will only trust on the results of the execution of the tests if I'm sure I can trust them. If they become red, but there's no bug, or if they are green and there's a bug, I will start not trusting my test suite. Yeah? So you need to put some effort in the whole, in the bigger picture of testing, which is you need to make sure your test suite is always in a state that people can trust the results. And this seems a very stupid thing to say, but crazy stuff happens in the large scale. One of them is what we call flaky tests. Flaky tests are tests that if you run them twice, in one execution the test will pass, and on the other execution the test will fail. Of course, a very bad flaky test is not the one that, if you run it passes, if you run again it fails, because this is easy to be detected and you can take action. A very bad flaky test is a test that really fails 1 out of 300 times that you run your test. How do you detect that a test is flaky? And it's just flaky, and it's not because you just introduced a bug in your application, right? This is a very big question. You see companies like Google and Facebook investing hard on techniques to identify flakiness. Even Gradle, so for the people in the Java world, Gradle is a famous building tool. Gradle has features to help you identify flaky tests. So it keeps percentages of how often a test failed in the past, how often it passed, to help you take decisions. I can't remember the number by Google, but Google reported numbers like I think 0.1 or 0.2% of their tests present flaky behavior at some point. 0.1% of tests at Google, we're talking on the scale of hundreds of thousands, right? So that is just a lot. And they will happen in real life. There are different cases, reasons for them to happen. If you're curious about this, there's a sort of a recent paper, 2014, where they try to classify reasons for flakiness in the wild. And then, as you can imagine, concurrency is a good one, right? So if you're testing a concurrent program, things happen, right? And then you get flakiness. Async await, so your test has to wait for something to happen before continuing, and your test has a 1 second timeout, but then the thing happens in 1.01 seconds, and then your test breaks. So this one, I think it's very hard to solve, and if you're tackling a concurrency problem, well, good luck. This one, you can understand a little bit more about your program and maybe fix, right? You think of better timeouts and etc. This one is the one that I think we should never, ever accept. That is test order dependency. So depending on the order that your test suite executes, the results of your tests are different. So in your machine, when you run your tests, maybe if it's a small program, you're probably executing the tests in a linear order. Your testing framework, if you look at the documentation, I'm not sure in other languages, but in Java, JUnit doesn't really officially give you an order. So you should never depend on the order of the execution of the tests. It's more likely that in your machine it's always executed in the same order, but you should never bet on this. But in large scale, what happens is we execute tests in parallel, right? Because we have to scale. I told you it takes hundreds of hours to run our test suite. So what we do, we put lots of machines to run. Hey, you run test 1 to 10, you run 10 to 20, and this is random. So you don't want your tests to break if you just run them in different orders. Regardless of the order, you want your tests to always pass. And this is an easy one to fix. Usually, if you have this test order dependency problem, what's happening is maybe, a test puts some data on somewhere, which the other tests also then access, and then things crash, right? So imagine you're running a test that expects one item in the database, you put it here, this other test expects one item in the database, but then when it looks, there was an item there before, so now it's 2 items instead of 1. These kind of things may happen. And as the paper says, if you just clean shared state between test runs, you're more likely to fix this stuff. So the lesson for you is, if you're creating a test suite, make sure that your tests are very polite and they clean up all the mess that they do. And maybe they even do some checks to make sure that the system is on the state that you want so that your tests don't fail without you knowing, right? An elegant fail is much better than a fail that you have to put a developer there to understand why it failed. Now, in practice, how do we survive with flaky tests? We strongly monitor them, and as soon as you detect them, you take them out of your test suite. Facebook has an interesting and very strong approach against flaky tests. As soon as the CI in Facebook detects that a test is flaky, it warns the developer that created the test. Hey, your test is flaky, my friend. Do something. If you didn't do anything after a few hours, the CI of Facebook deletes your test. Simple as this. Your test is flaky, you don't want to fix it. Okay, we're going to remove it from the CI. Because if it's flaky, it's going to give us wrong signals, and we don't want this. At Agin, we are not as opinionated as Facebook. What we do is we rerun the tests. So if we execute a test and then we see that the test fails, we try to rerun the test. Maybe in the second time it will pass. Very pragmatic approach. I'm not saying it's the best, but maybe it's a way to reduce the flakiness there. So you put it to run again, and then you notify the developer, and you still get the green signal from your test suite. If it doesn't happen, we move this test to another test suite that we know it's a flaky test suite. And hopefully the developer one day will go there. We call it the test flaky cemetery. It will go there and put this test back to live in the main testing pipeline. And believe it or not, it happens a lot, right? Lots of tests. We detect lots of tests. I'm not going to say daily because I don't have the numbers, but very often we detect a new test that is now presenting some flaky behavior. So pay attention to them. They will happen in large scale. And finally, I think I added this in the end because of a recent discussion that I had with an engineer. That is, if we're putting all this effort in making tests easy to be written, or if it really start to divide to conquer, right? So you're testing smaller units instead of very complex stuff altogether, then maybe you're going to have that impression that your tests look stupid. But what I want to argue is if your tests are looking stupid, this is a good thing because you worked for that to happen. It looks stupid because probably a lot of things are happening behind the scenes so that the test looks stupid. Like this one. This looks very stupid. You probably looked at it and you thought, what a stupid test. But it looks stupid. It looks very simple because we put a lot of energy in making it look like this. So I'm not saying there are no stupid tests. There are stupid tests, right? Tests that are not really giving you value. But when you look, the test code itself has to look stupid. This is the best test code you can have. That was it. Folks, a lot of it is in my book. Hopefully I gave you a different perspective on the book. I'm open to questions. Thank you.
If you have some questions, I'll pass that. This is for the live stream.
Yeah, I had a question. What sometimes happens is that you have a correct code, which is also tested, and it has, for example, 25 test cases, and then some trivial change need to be made to the code because the functionality, the required functionality changes. Let's say the number should be negative instead of positive, so you should multiply it by -1 or something like that. But then all your test cases fail, and sometimes then you spend more time fixing your test cases than fixing the actual software.
Yeah.
And sometimes that is really becomes a trend. So do you have any opinion to avoid those situations?
Very good question. And also a big pain in many systems out there, right? So your tests, in a way, are coupled to your production code, right? Because your tests make call to the production code, and if you change something in the production code, maybe your test code breaks. And the worst scenario is this one. You make a very simple change in production that takes you 5 minutes, and then you spend 20 minutes maybe fixing compilation errors in your test code or fixing assertions and etc. I think the suggestion there is to make sure your code is as least coupled as possible to production. There are many ways to do this. So for example, say you noticed that passing inputs to your program is something that tends to change a lot. You're still, you didn't find the precise design for your production class, so this is something that is changing a lot. Maybe you can try in your test code to maybe isolate this data creation process in one place so that you have to change just one method instead of 10. Like you're never going to avoid changing your test code when your production code changes, but what you want to do is to reduce it. Another tip that I have to myself is if I feel like I'm writing a production if I feel I'm writing test code, that whenever I change something in production code, I have to change test code, this is not good. And usually the way to fix this is to test this component at a higher level, maybe 2 or 3 components together, like from a bigger perspective. Because then the bigger your test is, the less your test knows about the component that's under tests. So this is something you want to also take into consideration, that your tests know very little about your production code. But you're going to experiment, right? You're going to make a mistake, and then you're going to learn from it, refactor your tests so that it will hurt you less the next time.
What do you mean in this case with production code? I mean, sometimes you can have, suppose we're working on a project that is not yet in production yet. It's it's new, but then some product owner didn't pay attention, and some requirements just simply change, right?
So production code for me, I wasn't really thinking of deploying to production, but like you have test code, and this test code tests something. It tests code.
Ah, sorry.
I'm calling it
so
production code.
Real code.
Just code. Yeah. This is definitely something to pay attention. Yeah. This is why, by the way, some people are favoring what they call use case testing today. That is, you don't want to test one unit because then it's too small and maybe your tests will be too coupled. You want to test the whole use case because then you make a call at use case level, and at this level you cannot be super coupled to the code. Something to consider.
I had one other question, if I might, about the flaky test cases. Yeah. So, in what you talked about, it was mainly about of your flaky test cases. Then your test cases are probably wrong. But you can also have flaky software, right? That maybe only on even hours it produces a bug, and then you test on random moments. You get sometimes or not.
Yeah, very good point. Maybe your tests are perfect. What sucks is your software system, the system under test, right? So that can happen. And then you're going to learn from your tests, and you're going to fix your software system. So in a way, the tests did a good thing to you, revealing the flakiness. I think the problem really happens when your software is stable, and you cannot trust your tests.
Shall I pass it around?
Thanks. So a few days ago, I watched a talk on so-called fuzzing, which is just basically having a program throw random inputs at your program and seeing whether it crashes. And I was thinking, what is the case in which you would actually be using it for your company? It obviously won't actually test every single edge case a human can think of, but it can test stuff that a human wouldn't think. They're kind of like opposites in one way. So I'm not sure how you would be using them.
Yeah, very good question. So what you see nowadays is companies relying also on intelligent techniques, as we call, like fuzzing or search-based software testing, or even deep learning nowadays, looking for bugs for you, right? And why do you want this? Because as a human, you can only see so far. Even if you apply systematic testing and boundary testing and blah, 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 your test cases will be limited to your capacity as a human. What is very cool about fuzzing or search-based software testing is that then computers are looking for bugs for you. So you give them some hints, and they look for bugs for you, and they find bugs that you don't. So they complement your tests. So I don't think fuzzing or AI for software testing will replace these type of tests. They will complement your tests. And fuzzing is interesting because fuzzing is something that exists even before AI in a way, right? And it's just this very stupid idea that let's just keep throwing random stuff to the program and see how the program handles this. And it does find lots of bugs. So if you can add this to your process, usually fuzzing is very tricky because you have to implement a tool for yourself. There's no generic fuzzing tool that are, but for large-scale software systems, you see companies developing their own. If you can invest on these things, go for it. All the cool companies do, Google, etc. If you're curious about AI for software testing, Google for Sapiens, like the Sapiens, the word Sapiens, but I think it ends with a Z. Sapiens Facebook. It is a project at Facebook that was, it was an academic project at University, Imperial College London, created by a professor there and a PhD student. And the tool basically tests the mobile apps from the Meta group. And the tool uses some AI to randomly explore the application. And if it finds bugs, it creates an issue about the bug with all the steps. And nowadays, they even worked on automatic program repair. So as soon as the test case is created that shows that the program fails, another AI tries to find the fix. right? That will fix. And why does this work? Because most bugs we write are very stupid, meaning if you just change something in your production code, your test will pass. So you see Facebook doing this. Sapiens is the name of the project.
Yeah, I had a question about the flaky code. How do you differentiate between, let's say, you got a test that is one-off that only sometimes comes back as an error and sometimes doesn't? How do you differentiate between flakiness of the tests and flakiness of, or just bugs in your code?
Yeah, no one knows. And that's what it makes so hard, right? There's no clear algorithm to decide if your test is flaky or if it's because you have a bug. What you see is people taking some probabilistic approaches, trying to understand how often it fails. You change class A and then a test that fails is something really far from class A. Maybe, that's a hint for you that this test is flaky. So you see people using machine learning now to try and predict if a test is actually flaky or not. But that's one of the open questions.
Thank you. I would like to ask of the part that I didn't know. Like as you said, you did a vote. Like people knew about parts where test supplement development and knew less about tests finding bugs. So I also knew almost nothing about the part where test is for finding bugs. So maybe you can suggest what to read about it, or just like say what structural testing is. Yeah.
Well, you can read my book.
Thank you.
So the academics book that I mentioned in my presentation, they talk about this. You're going to get the slides afterwards, and then you can see there. Specification testing is the idea of looking at the specs, the requirements, and then diving into these requirements and understanding them. Boundary testing is looking at the boundaries, as I showed. The structural testing is code coverage. It's just a different name for code coverage. So you're testing from the structure. So when I mentioned code coverage, the academic name for code coverage is structural testing.
Thank you. Thank you.
My pleasure.
Makes sense.
Oop.
Hello. So maybe, yeah, okay, I'm just going to ask it, but do developers who test and are able to test, do they also earn more money?
Do they earn more money? That's a very good question. Money is tricky, but I definitely feel that developers that consistently write more tests are the senior developers in the team. I think as a novice, maybe you're still struggling to write tests and learning how to do this properly. I think one characteristic of being a senior engineer is that you can just write tests and you don't have to even think about it. And maybe seniors are more rewarded than novices salary-wise. At Agent, for example, we put explicitly that thinking of testing is something that we expect from all engineers there. It doesn't matter the level. And you see other companies with the same approach. I hope that answers the question.
Yes, yes it does. It's just when I was searching for a job, then yeah, most vacancies did not specify, hey, you need, or we expect you to be able to test software if you're searching for a software position. So.
Yeah, what I see in those cool job offers that you see, for example, from Agent or Dutch companies, Coolblue, Bol.com, etc. They put like you have to be very aware of how to write high quality code and best practices and test-driven development and etc. I don't think they say you should know specification testing because that's too boring, but they do talk about high quality code, and to me that's testing is maybe the best way to get there.
So here you talk about the testers have access to the source code, but what do you think about bug bounty programs? They don't have access to the source code, right?
No, usually no. I think you can approach tests from many different angles. bug bounties are an interesting one, where you're just basically giving the responsibility of finding a bug to a third party, right? It's usually someone that doesn't belong to the company to do this. I think the generic message about this is that I think we all know that testing isn't perfect. And you can put as much effort as you can in writing tests as a developer and making sure that your program works. But as soon as you ship it to production, there will be bugs. So what can you do beyond testing? You can have bug bounty programs. Companies invest a lot in monitoring, right, to understand and detect the bug as soon as possible. So I hope that answers the question. So I really appreciate all sorts of efforts you can do related to testing, even if it means that you don't have access to the source code.
So what would be, in your opinion, an effective strategy to, become good at testing?
Yeah, practicing.
Yeah, okay.
Right?
Yeah.
I think it's all about trying to write tests all the time, and try not to, fall into the trap of it's too hard. Let me just forget about testing and move to the next feature. I think if you have the chance to, I have time to practice and learn testing, you should do this. I think I started to be able to really think more holistically about testing when I didn't have to think about writing tests anymore. I could just, I'm programming my class. I know precisely how to create a JUnit test for it. And then as soon as this became mechanical to me, this allowed me to reflect about bigger things. And I got there by just practicing a lot. In my testing course at Delft, what I do to students is I give them, 60, 70 small programs, and they have to write tests. In a deliberate practice kind of way. Very isolated problem, you write your test, you get feedback, you go to the next one. It has to become a mechanical thing for you.
So a lot of people can probably think of programs they've written in the past which they think are pretty hard to test, like for example games. It's pretty hard to test a game for every single thing a player can do or every single interaction. So is it still worth it to test that kind of stuff which is really hard, which doesn't have a clear API or is just really random?
Yeah, I think you have to be super creative in cases where writing tests are very difficult, and games are a good example, right? So you can unit test lots of stuff in a game, but in the end what matters is if you can really walk with the player, and when you shoot someone the monster dies, right? And these kind of things. So I think that the whole effort is to invest in infrastructure that allows you to do this. There's a beautiful video on the internet, is how Minecraft uses Minecraft to test Minecraft. So they have lots of test cases where they really put a Minecraft game to run and they know what to expect in that specific game. I know Microsoft has lots of monitoring systems in place when you're playing, what is the famous Microsoft shooting game that you only have for Microsoft platforms? Halo. When they are testing Halo, they have monitoring systems that as soon as something bizarre happens in some online game, a developer gets lots of debugging information about it, fully anonymized and etc. So I think in these environments you have to be super duper creative. You see this also happening, for example, how do you test medical devices? How Philips tests medical devices, right? So they do write lots of tests for the components, but they also think holistically. And I think that's the beauty of testing, right? It's really contextual.
Thank you.
My pleasure.
Do we have any other questions from the auditorium? No? Okay. We also don't have any questions from people online, so I guess we will wrap it up. So thank you.